Hey there, science fans! Today we're diving into the fascinating world of material science. Buckle up, because we're exploring three big topics: corrosion, cement, and lubricants. These might sound kinda dull, but trust me, they're anything but. Corrosion is like the silent destroyer. It's what happens when metals slowly break down, like that rusty old bike in your garage. Cement is the backbone of buildings and bridges, holding everything together. And lubricants? Well, they keep things running smoothly, literally. Without lubricants, our cars would seize up and our bicycles would be a whole lot harder to pedal. So, get ready to explore the amazing properties of these materials and how they shape our world. Let's get started. First up, let's tackle corrosion. Corrosion is like a bad case of the sniffles for metals. It happens when a metal reacts with its environment, causing it to weaken and deteriorate. Think of a rusty nail. That's corrosion in action. There are two main types of corrosion: dry corrosion and wet corrosion. Dry corrosion, as you might guess, happens in the absence of a liquid. It's all about those sneaky gases in the air reacting with the surface of a metal. Several factors can speed up dry corrosion, like temperature. Just like you might feel more sluggish on a hot day, metals are more likely to corrode at higher temperatures. The type of metal also matters. Some metals, like gold, are very resistant to corrosion, while others, like iron, are more prone to rusting. Now let's zoom in on how dry corrosion actually works. Imagine a metal surface. It's not perfectly smooth. It has tiny bumps and valleys. When gases in the air, like oxygen, come into contact with these surfaces, they react with the metal atoms. This reaction forms a new layer on the metal surface, kind of like a thin skin. This process is called oxidation and is the most common type of dry corrosion. The type of layer formed depends on the metal and the gas involved. Sometimes this layer is protective, like a suit of armor, shielding the metal from further corrosion. Other times it's porous and flaky, allowing the corrosion to eat away at the metal underneath. It's a constant battle between the metal and its environment. Let's talk more about oxidation corrosion, the heavyweight champion of dry corrosion. When a metal reacts with oxygen, it forms a metal oxide layer. The Pilling-Bedworth rule helps us understand whether this oxide layer will be a good guy or a bad guy. Think of it like this: if the oxide layer is too small, like a shrunken sweater, it won't protect the metal underneath. If it's too big, like a puffy jacket that's too large, it'll be brittle and crack under pressure, exposing the metal again. The Pilling-Bedworth ratio tells us the volume of the oxide formed compared to the volume of the metal it came from. A ratio close to 1 is ideal, meaning the oxide layer fits just right, providing good protection. Section 5. Gaseous corrosion and hydrogen embrittlement. Oxygen isn't the only gas that can cause corrosion. Other gases like sulfur dioxide and hydrogen sulfide can also react with metals, leading to corrosion. These gases are often found in industrial areas and can cause serious damage to structures and equipment. Hydrogen, believe it or not, can also be a troublemaker when it comes to corrosion. Hydrogen embrittlement is a sneaky type of corrosion where hydrogen atoms infiltrate a metal structure, making it brittle and prone to cracking. It's like turning a strong metal into a fragile piece of glass. Section 6. Liquid metal corrosion. Now let's dive into another type of corrosion: liquid metal corrosion. This happens when a liquid metal like mercury comes into contact with a solid metal. The liquid metal can dissolve the solid metal, weakening it over time. Think of it like dropping a sugar cube into a cup of hot tea. The sugar dissolves into the tea, and eventually the sugar cube disappears. Liquid metal corrosion is a serious concern in industries that use molten metals, like nuclear power plants. Section 7. Wet corrosion. An introduction. We've covered dry corrosion, so now let's dive into its partner in crime: wet corrosion. As you might guess, wet corrosion happens in the presence of a liquid, usually water. Think of the rust you see on cars or ships. That's wet corrosion in action. Wet corrosion is a bit more complex than dry corrosion because it involves electrochemical reactions. This means that electrons are moving around, creating electrical currents that contribute to the corrosion process. There are several types of wet corrosion, each with its own unique characteristics. We'll be exploring these in more detail later on. Section 8. Chemical corrosion. Chemical corrosion is like a direct attack on a metal surface. It happens when a corrosive substance, like a strong acid or alkali, comes into contact with the metal and directly eats away at it. Imagine spilling battery acid on a metal surface. That's chemical corrosion at work. The severity of chemical corrosion depends on the aggressiveness of the substance and the resistance of the metal. Factors like temperature and concentration also play a role, just like with dry corrosion. Section 9. Electrochemical mechanism of wet corrosion. Let's dive deeper into the fascinating world of wet corrosion and its electrochemical nature. Remember those electrons we talked about? Well, in wet corrosion, they're the stars of the show. Wet corrosion involves two main reactions, an oxidation reaction and a reduction reaction. In the oxidation reaction, the metal loses electrons, becoming a positively charged ion. This is where the metal starts to break down. The reduction reaction happens simultaneously, where another substance in the environment gains those lost electrons. This creates a flow of electrons, forming an electrical current. It's like a tiny battery operating on the metal surface. Section 10. Theories of wet corrosion. Scientists have developed several theories to explain the different ways wet corrosion can occur. One important theory is the differential aeration theory. This theory explains how differences in oxygen concentration on a metal surface can lead to corrosion. Imagine a drop of water on a metal surface. The area at the edge of the drop has more access to oxygen than the area in the center. This difference in oxygen concentration creates an electrochemical cell, with the area of higher oxygen concentration becoming the cathode and the area of lower concentration becoming the anode. Corrosion then occurs preferentially at the anode, where the metal dissolves. This is why you often see more corrosion in crevices or under deposits where oxygen is limited. Section 11. Corrosion control methods. Corrosion might seem inevitable, but fear not, we have ways to fight back and protect our metals. One common method is using protective coatings like paint or plating. These coatings act like a barrier, preventing the corrosive environment from reaching the metal surface. Another strategy is to use corrosion inhibitors. These are substances that are added to the environment to slow down or prevent the corrosion process. Cathodic protection is another effective technique where a more active metal is connected to the metal we want to protect. This sacrificial metal corrodes instead of the protected metal, like a bodyguard taking the hit. Remember, prevention is key when it comes to corrosion.